Good afternoon, everybody. My name is Santeri Paavolainen, and I'm presenting here talking about Interledger stuff. This work has been created in collaboration with my colleague Tommi Aelo and Professor Pekka Nikander from Aalto University in Finland, Department of Electrical Engineering, School of Electrical Engineering, Department of Communications and Networking. So I have an audience participation question. I think the first one you will find easy to answer. Has anyone here heard of blockchain? Hands up. Okay, I say quite a lot of people who probably need an introduction to blockchain then. How many of you have need to be particular with this. How many of you have actually worked on public blockchains such as Bitcoin, Ethereum, or something else? Hands up. Okay, quite a few. How many of you have worked with sort of internal or private or consortium ledgers? Also quite a few. How many have worked on multi-party ledgers? Yeah. That working better? That recording, okay. No hands? Multi-party ledgers? Okay. We don't have 90 minutes anymore to cover quite a lot of things. I'll try to make sure that we have some time at the end for questions, but please do not hesitate to ask, stop and ask during the presentation. I might say that I'll cover it later, or please come and ask me after the presentation. I'll be also on the demo booth demonstrating a use case of an Interledger over there. So you can come and visit and see me there. So, quick agenda, some introductions, backgrounds, motivation, Interledger in practice, actually providing an example of a specific Interledger type of applications. Different Interledger approach, typical use cases, and summary. I'll go through a bit of blockchain basics, cryptographic primitives. I think most of you will find this pretty familiar. I'm sorry, I don't have a talking monkey or anything to make it funny, but let's go on. Yeah. So I'm pretty sure that I've been using, and I will keep using the terms blockchain and distributed ledger technologies pretty much interchangeably. So while I know that they are not the same, let's just agree for the sake of this presentation that they are within the measurement error pretty close enough that we can use them interchangeably. My view of why I think for a lot of the applications that I use or try to use, this is a research work after all, I'm not guaranteed any success. So many of the ideas where I try to use DLTs, especially in conjunction with IoT devices, is because of the immutability and distribution and decentralizing properties you have with ledgers. Again, let's agree with the caveat of approximately within measurement error. There's all are other uses, other rationale for using blockchains. But this is still a good starting point for most cases. Another pretty important distinction that will come along when we are talking about Interledger operations and the motives of those Interledger operations is making a distinction or division between public and permissioned ledgers. And again, you can argue different cases, but from my point of view, the most important critical aspect is that public ledgers don't have admission control. So anyone can act as a peer, which sort of previously no good Sybil protection mechanisms existed, but nowadays we have Nakamoto consensus sort of to work around that. Whereas permissioned ledgers, you have some sort of an admission control through some policy, whether that's a centralized policy, hierarchical policy, pair policy, or whatever policy. That's a whole other thing. But the critical thing is that you have some sort of an admission policy, how one can become a peer on the network. Yeah. So next up is a bit more background of what kind of DLTs exist and how they are operated, and then a brief introduction to smart contracts, and a recap of some of the needed cryptographic primitives. So I've drawn here public, consortium, and private ledgers. And how are they different? So I mentioned before that public or permissionless ledgers don't have any kind of, don't really have an admission control mechanism or policy governance model for that available. So for that reason, most public blockchains such as Bitcoin, Ethereum, and many others use typically Nakamoto consensus and are Nakamoto consensus blockchains. And on public blockchains, each node or each peer is somehow proportionally, has a proportional rights to the overall number of participants on the network. And since the decentralization factor is typically quite high, then it's usually pretty small number per peer. Now, what is proportional representation of proportional rights very much depends on the actual consensus mechanism, whether you are talking about hash rates or staking or whatnot. But the idea still retains that peers are somehow proportionally everybody, all nodes, all peers on the network have some sort of stake or rights on the network. However, in contrast, we have these permission DLTs and consortium and private ledgers, and that's how I use the definition, is that consortium ledgers are, or actually let's start with private ledgers. Private ledgers are essentially, if I have a private ledger, I own the private ledger, I'm the governing body of the private ledger. I decide who gets in, I decide who goes out. Since this is still a DLT, I can't fake stuff, but I can still do governing on the ledger. Versus consortium ledgers, you can think about classical business consortium where there's a few, but more than a couple participants or peers on the network. So typically the decentralization factor for consortium ledgers is somewhere tens, maybe a little bit less, maybe a little less, more. But one of the more interesting features, of course, in consortium ledgers and also private ledgers is that they can use Byzantine consensus models instead of Nakamoto consensus models. And that especially in the context of consortium operations is a very nice property to have, because it means a lot fast, lot better, lot higher throughput, much smaller commitment time, etc. Nice properties to have. Then, pretty quickly, I'm sure that you are familiar with most of these Bitcoin, Ethereum, maybe not guard time. Then there's Ripple Corda, Hyperledger Fabric. So while I said that there are permissions and permission, sort of identity-based or permissioned proof of work, Nakamoto consensus, Byzantine consensus, there's sort of still a bit more leeway in here, a bit more on how different ledgers, for example, approach identity, whether the identity is more like a strict sense that you need a specific identity to operate at all on the ledger, or whether you can have some sort of a shades of gray regarding how hard that identity must be on the ledger. And then, of course, you have things like Intel SGX extensions, which sort of are not entirely without identity, because the chips have an identity and they need some sort of a centralized trust model. But then again, a lot of their applications are not. So there's lots of variation in the field. Okay. The reason why I'm talking about smart contracts is that they are very used in many interledger operations as sort of a building blocks for building those operations. So smart contracts are programs that run as part of the blockchain, on blockchain, in blockchain. The smart contracts can have internal state that is internal, that is essentially stored on the blockchain itself or DLT ledger. And Ethereum is probably the most known of DLTs supporting smart contracts. You can pretty much guess that since Ethereum is a decentralized and distributed system, the idea of running a program on a blockchain that potentially is someone else's program running on your own computer is a bit, does require a bit of security and isolation properties. And for example, Ethereum provides those properties through defining an explicit Ethereum virtual machine that is, first of all, completely deterministic, but also completely isolated from the host system. So any smart contract can access only state within the blockchain itself. It cannot do any file operations, anything like that. So it is essentially safe to run smart contracts on any host computer. Also, in general, if you have a smart contract, they have to be fully deterministic, because otherwise you could not have a situation where other nodes actually validate the computation. And that is still even the case of Hyperledger Fabric, or chain code as Hyperledger Fabric calls smart contracts. And in contrast with Ethereum, where in Ethereum anyone is equivalent on the network and anyone can create a smart contract. In Hyperledger Fabric, since it is a permission blockchain, actually the chain code installation is done by administrators, and that's a sort of a manual step. In contrast, because they have access to the source code and can validate and do independent auditing of the smart chain code itself, they can actually don't have to have an explicit virtual machine and can run directly on the machine, sort of on the machine level using Java, Go, and other runtime environments. Of course, in implementing chain code in these languages, it is a bad idea to use any kind of randomness, first of all. And secondly, you might not get a good viewing by the admins if you put any file operations there regardless. Regardless of these differences in the implementation of smart contracts in different platforms, they operate on all, essentially it's the same model. You have a smart contract that is installed somehow, let's skip how for now. That doesn't terribly matter in this context. But you interact with them by sending a transaction to the ledger. And if your transaction is accepted by the ledger, blockchain, Ethereum, Fabric, whatever, then the actual call and the results of that call become part of the ledger itself. So they become permanent records of the fact that someone has called a smart contract and it produced these results. And also any state changes in the smart contract itself or other smart contracts will also become permanent record on the ledger. Since smart contracts operate in a Turing or close to Turing complete environment, they can do any kind of computation that they want. They don't have file access, which is not a good idea, not having a file access on a host computer. But that means that they can do quite a lot of highly complicated things. Any kind of essentially a policy that you can encode in deterministic computation, you can implement in smart code, smart contracts. So for example, you could have a smart contract that maintains a list of maybe members of some set. and you have a mechanism where n out of m existing members of that set can vote new members in, but maybe only on the first week of each month, or any arbitrary policy decision you can calculate in. Similarly, you could have like an asset release from a smart contract based on an n-party multi-signature, but then encode sort of a cool-down period after this transaction that must be taken before the actual release occurs. Maybe there's a even larger majority could actually undo the transaction. So you can have these kind of different policy mechanisms, different implement more or less arbitrary policy mechanisms. That's also comes pretty relevant when talking about interledger operations. Next. And final piece on these basics. How many of you have not heard of cryptographic hash functions? I guess I can more or less skip this. But overall, why we talk about hash functions is that they are basically a basic tool, basic utility mechanism for used in digital signatures and blockchains. And later, when I talk about hash time lock contracts and hash time lock agreements, you can guess that the hash there is pretty relevant here also, or comes out of this. Oh, I did have one slide more. So, the common idea of public key encryption or public key cryptography or asymmetric cryptography is that you have a public and a private key. And originally the idea is really that you publish the public key, people can encrypt data, send you the data, and only you can, using the private key, decrypt the data, so it is safe during transmission. That's not how it's usually used on blockchains. Of course, you can use it that way, but it's most of the time, actually what happens on blockchains and DLTs is that you actually use a private key to generate a signature of a data. And then anyone with access to the public key can actually verify that the holder of the private key signed the data. And that, of course, is a basis for many operations in not only public blockchains, but also permission blockchains, where you need to have access to a private key to be able to create transactions on the blockchain, because you need to sign the transactions. And then also, in most DLTs, also this public key acts as an address for the blockchain or DLT, or is derived from one. For example, Ethereum addresses are 160 bits, 20 characters, 40 hex bytes, which are, if I remember correctly, they are derived from a truncated hash of the public key. I might remember wrong, but anyway, that's the idea, that you can, anyone holding the private key linked to specific address essentially has full authority of that address. They can sign transactions, generate transactions on behalf of that address, or they are the address in a way. There's of course a little bit more details, but that's a general overview of how cryptographic signatures are used in DLTs. Okay, that lasted about 17 minutes. So now can we come to the bit of what I know that I have not yet defined what is interledger. I'll come to that shortly. But before going to that, I will torment you a little bit more on why interledger. So you may have noticed a ledger, the blockchain called Bitcoin in the press, maybe sometimes. That's a pretty big ledger. I guess it's even still now the biggest market cap ledger. So you have the question, why would you need another one? Why is one not sufficient? Okay, that's sort of a leading question. You may also have noticed that there is a tons of different blockchain DLTs generally. Public, and since by definition any private or mostly consortium ledgers are not public, we don't have a definite number of how many of those actually exist in the wild. The best guess, of course, is there are more of those than public ledgers. So then you have multiple arguments why one ledger is not sufficient. So the first comes out of just a reality check. There already are multiple ledgers, and there is no definite, clear, single majority winner. So you already have the reality that you have to deal with multiple ledgers anyway. So why not just bite the bullet and accept that you have to do multi-ledger operations in some manner eventually. Then you can also have requirements on a particular use case that are met differently by different technologies. So it's not easy to imagine or not in practice realize a situation where your needs, for example, internally in a company and internally in a consortia are in odds with, for example, a public ledger technology. Similarly, you may have a situation where you are in a consortia and you join a consortia, and the consortia, after many heated debates of whether we use a Hyperledger Fabric or Hyperledger Capric or Hyperledger Bagbrick or whatever we want to use, come to a conclusion. And then you realize that it's not the technology you are using yourself. And then you have also complex applications. So what this I mean that you potentially have a complex application that operates on a ledger. So if you want to expand that to multiple ledgers, are you going to silo then build a new copy of one? So this is for the same application for Bitcoin, this is the same application for Ethereum, this is the same application for the Ethereum Classic, and this is the same application for Ethereum 2020, and this is the, or are you going to essentially do a multi-tenant hosting and run a single application that can then work across all of these ledgers? And how do you bind those ledgers together? And let's not get started on performance at all. So very quickly through this, the point is not, this is not a beauty contest. You can get red-faced all you want about the confirmation delay of Bitcoin, but it is the biggest and baddest and meanest of everything, so you got to live with that. The important point is that there are variations, even on these pretty simple and straightforward metrics across different ledger technologies. And in some applications, a long confirmation delay might not actually be a bad idea. It might be actually a positive idea on some use cases. But then again, you might need some other stuff from your ledger, or the other stuff might be actually something that you definitely do not want from your ledger. You do not want your ledger maybe to have a capability to forget for some use cases. In consortia, you might actually not want necessarily be able to, for a majority to edit yourself out of the picture, for example. And this is not even including many of the other dimensions that are feasible on this comparison. So the end situation is that at least from my point of view, I believe that it will become very difficult to operate on a single ledger alone in larger business and larger business ecosystems. So, okay, now I promised I'll talk about what is actually Interledger. So, Interledger is not ILP. seems to be a common mistake thinking about the interledger operations are ILP or interledger protocol or interledger payments. The core concept of interledger operations is really to make it possible to have some guarantees of commitment and not atomicity because they can't happen simultaneously, but some shared understanding of a common commitment protocol across multiple ledgers. And pretty simple use case to what we want to avoid is that when I'm sending you ethers, I send you 10 ethers, then you wait for confirmation, and then you send me, then you keep the bitcoins. So that's the scenario I want to avoid, and generally everybody wants to avoid. So what we want to do in this kind of a simple trivial case of multi-ledger operations is that I send you ethers, but only if you deposit me the agreed amount of bitcoins. So there's sort of the magic that the interledger operations occur, that we have some mechanisms to enforce, not necessarily these kind of swaps alone, but multiple categories of operations. Even this is a bit generalization. Once we get to ILP, there are things on ILP which sort of break that model, but you could think about the general goal of when we are talking about interledger operations is try to avoid creating unnecessary trust and use the properties and technologies and cryptographic primitives available to us to minimize the amount of trust necessary. Sometimes you can't always avoid that completely. But we still want to avoid this blind trust scenario that is in the first scenario. Questions? Maybe I should use the same technique I use in my classrooms. I just pick a volunteer. No volunteers yet? Okay, I'll let you go for now. Before going through many different types of interledger approaches, I'll walk you through one single example, using one single example type of interledger approach. So this is not the interledger approach. There is no the interledger approach. There's just multiple ones of them. This is highly trivialized and very much abstracted use case, but I hope it gives some insight. So I have the demo, by the way, is also there of this one. So we want to pay over a public blockchain for access to an IoT device. If you are familiar with Ethereum, you probably know that it takes at least 5 gigabytes of state space. Bitcoin takes about 200 gigabytes of UTXO set. Those don't fit in an IoT device, period. So then you can go to light protocols, etc. But an alternate mechanism is that instead of trying to connect the IoT device, or a lamp in this case, RGB lamp, to the public blockchain, we just connect it to some other ledger that is much more IoT friendly. Because that is not the public blockchain, we can choose a ledger that is IoT friendly. We are free to choose it at that time. But we pay in the public ledger, and we do some magic interledger stuff to actually make it happen across these gateways without creating unnecessary amount of trust required in the system. So if we start with it, again, with the general problem, IoT device, public blockchain. The goal is really to get sort of money out through the public blockchain. So we will want to be paid like that. But as said, we have this sort of a chasm, a reality resource requirements versus resources available constraint between these two. Which is essentially saying that public blockchains generally have a high CPU demand, have a high storage needs, require a lot of network bandwidth. And especially on if you are talking about cheap or mass-produced or high-profit, high-margin devices, you don't have tons of money to put into the actual hardware. So you have a constrained hardware. You may have a sort of like just 200 megabytes of storage and not gigabytes. You may have a narrowband network running there, which means that you can't really transfer all the blocks anyway. So just to think about if you have a $10 internet connected device that is its retail price is $10, how can anyone guess how much the device manufacturing is going to cost? Any guesses? Okay, the sort of a rule of thumb is that manufacturing costs are 1/10 of the retail price. So a $10 IoT device has $1 to use for manufacturing. And that includes all manufacturing. That includes the manufacturer's markup. It includes the CPU, it includes the case, it includes the packaging, it includes everything else. So the chip itself is probably going to get 10 cents at most. So you can already see that it's not, when we are talking about mass-produced IoT devices, we are talking about really, really constrained devices. So anyway, this is a sort of the desired goal state. We want the IoT device to operate on permissioned ledger. But this doesn't sort of work for if we have the end customer and how do they actually operate on permissioned ledger. And there's multiple reasons why this would not work. That we asked, let's ask the customer or let's ask the user to just connect to our private ledger or our consortium ledger. And first of all, there's the general problem of DLT software adoption, which you probably are aware that if you count the number of MetaMask or Mist or Ethereum or Bitcoin wallet users, you get, comparatively speaking, to a very low number of people compared to the number of internet users in general. And if we asked this small set, which we, of course, everybody hopes that will grow larger over time, but if we start with a small set and ask that set to connect to our private network, then we are making that set even smaller. So you can see the general problem of DLT software adoption, and we definitely don't want to make that a bigger problem in our case. But then you also have the mindshare problem. Even if there was software connecting to different private ledgers, are you sure that they are really suitable for your choices? Because there's mind and market share still going around. Convenience is a big factor always. So if you just need to, I want to control this thing. It's fun and nice, and I want to play with it for a while. But if it requires me 5 minutes, 3 minutes, 2 minutes, if it requires me more than 15 seconds to set up, I'm not going to go do it anyway. Anyway, transacting on multiple ledgers always has liquidity and currency risks, and people will be aware of those. So if you ask me first to buy some tokens in here, then I need to I am really concerned about that as an investment too, and trust. How we can present ourselves as trusted for that user. How the user can be certain that we are not just fronting up a majority of consortium nodes and just shamming it. And the answer is really we can't. So we have to build on something that they already have a relationship, and that is what the public ledger has to be there for. I'm talking this about in a very consumer-oriented fashion, but you can make the same arguments to companies in general. Some to a somewhat lesser extent, but still. So, as again, from the topic of the talk, it should be obvious that this is the way we are going. And in this case, the simple idea is that the IoT device talks with the permission ledger, the end user or customer talks with the public blockchain, and then we have some sort of a gateway that bridges these two different layers. And note that we still assume that there will be direct communication between the device and the user in this scenario, because we have no wish to do like payment pre-setup, user interface stuff, control logic over the ledger. So the ledgers here are used only for payment and provisioning, essentially, transfer of control authority. So if we start with the initial setup, the user will be just browsing to the device. Okay, here's this option. I have an option of buying 2 minutes of access for this amount. Okay, let's select that one and select pay. And once the user starts the payment protocol, the device will generate sort of a token key and then hash it. Here comes the hashes. And sends the hash along with many other parameters that are required for this to work, but sends the hash to the user, and this goes directly to the user. So the next step is for the user to actually generate a transaction and send it to the public blockchain or smart contract. And in this case, of course, we are assuming that we have a smart contract already established on the network. It is public, and it can be certified or validated or assured by different parties, by the user themselves if they wish to. So they send the payment to the smart contract, which takes the payment in escrow. So this money is still not available for the device or IoT device owner. Then in the smart contract, okay, there's something missing from the animation. It should go smoothly over here. But anyway, it gets over, the transaction gets here, the gateway picks up the transaction, sends it to the private network permissioned ledger, and then the device picks up the transaction. So now the device has information there has happened a payment on the public ledger for this amount, for address to me, for this hash. And then it can check its own database payment records that yes, there was this payment, and dig out the actual token key. And from here, it just goes back, and back. And since the key itself is required to unlock the funds here, that means once a transaction ends up here, and by auditing the code, anyone then in this scenario could see that there is no mechanism here to release the funds to the IoT device beneficiary without providing a valid token that hashes to the hash that was previously there. So that's a hash lock agreement. Of course, the time lock here comes from the fact that you don't want these funds to be eternally locked here, so there is some sort of a time lock that after a specific period has passed, the user can actually reclaim their money back. Anyway, what happens, of course, again, the user gets the token key, someone gets their money, gateway operator gets their probably 30% cut from that money also, and then the user can use the token key to gain access to the device and then do blinking lights. There's some caveats and some more subtleties to this protocol security-wise, but that's the overall pictures of how things you can do sort of a payment verification on an independent ledger without actually touching the public ledger, but still receive funds through public blockchain. So this is just one example. Was just one possible example of how we can, what we can use interledger mechanisms for. But there's more. So as I said, that's just a single trivialized example using a single interledger approach. So these are some of the different approaches that I can actually one of the co-researchers' work that they've done on studying interledger approaches. And they identified different types of interledger approaches, such as atomic cross-chain transactions or atomic cross-chain swaps, sidechains, bridging approaches, payment channels, ledger of ledgers, and interledger protocol as a specific example of one type of approach. So all of these are interledger approaches, ways of transacting across multiple ledgers, and they have different pros and cons. They operate differently. So that's one of the things, that there is no single interledger. So let's go through them all in order. We'll use maybe 15 minutes for each. Then we should be out of here by midnight. A little bit faster. So atomic cross-chain transactions or atomic cross-chain swaps essentially originated originally in Bitcoin, and the interesting thing is that they were initially essentially workaround through Bitcoin's problems. A nice research project otherwise also, but in practice you might have noticed that Bitcoin has a long commitment time and is a bit difficult to operate and doesn't support terribly a lot of complex stuff. So the idea of sidechain, rewind, undo, started talking about sidechains because it's the next slide here. So let me backtrack and talk about atomic cross-chain transactions, not sidechains, which are the next topic. So essentially cross-chain swaps are just atomic swaps. I will give you Bitcoins on this network if you give me equivalent amount of ethers on the other network. And both parties have accounts on both networks. And that's just like atomic swap. I give you this, that, and we'll count to 3 and each one will release their hold on their assets. Actually, of course, in the case of Interledger, we use hash locks and various other mechanisms to ensure that this is actually either-or operations, so either both succeed or both fail. And the thing here is, of course, it does not require a trusted party. It does require some primitive scripting, and this means that it actually works on Bitcoin, so you don't need like smart contracts for this to work. But it is limited. You can already see how it is limited, that it requires that both parties have accounts on both ledgers, and they can need also an off ledger protocol to agree on what they are doing. But it works. So now we come to sidechains, which I accidentally started talking on the last slide. This idea of sidechains sort of is, well, side and main chain. There's a main chain that you think is the sort of the main stories of the assets that you are talking about, and side chains are mostly like the original one, but maybe with some a little bit different types of rules. And for example, this did originally come from Bitcoin world as a research tool and also as a workaround to slow commit times. So the idea in side chains is that you have so the main Bitcoin here chain might operates with its usual 10 to 20 minute commitment block interval, but you might have a side chain that has maybe 2 minute block commit time. And when you want to do quick transactions in succession, you would move or freeze your assets on the main chain and release them on the side chain, then operate on the side chain, do any kind of transaction trades you want, and then do the reverse again and get your assets back to the main chain, or if they are at someone else's possession at that time, of course, then you don't get to play with them anymore. There's some, again, sub-analysis on how this is actually works. But that's the high-level idea that you temporarily move your assets somewhere else where it can operate under different rules, but they still remain the same sort of same denominator, same assets, and then you can move them back. And there's actually multiple different sidechain approaches. So federated pegs are actually the original sidechain proposal, where you have the external entity which manages this transfer of freezing and unfreezing of assets is actually a Byzantine agreement of multi-party agreement. Requires multi-signature ledgers and gateways. I have merge mining that moves this sort of authority or freezing and unfreezing to actual miners. And then you got Plasma, Cardano settlement layer, etc. There's different ways you can implement sidechains in different situations. But they are very applicable in situations. For example, as an example, when Bitcoin was thinking about this called DMSS extension, changing of the, adding a new operation support to the Bitcoin core, that was actually tried first out in a sidechain. So there was a sidechain operating using these new opcodes and new rules. And that was a test bed of this operation. And it was not like a test net, but it actually operated on the real Bitcoins on the sidechain. So you could implement at least some advanced testing or actually advanced production systems in a sidechain, Bitcoin sidechain. Okay, bridging. I could say that this is more a bit like cross-chain swaps or side chains, but with the idea that you do not really have a party-to-party. You have equivalent peers. So one of the things about side chains is if the original chain goes away, so assuming that Bitcoin ever just vanished out to thin air immediately, somehow mysteriously immediately, and all data was lost, the side chains would be stranded and completely like useless. Whereas the idea is that when you are talking about the bridging, you have a equivalent or peer networks. So if one goes away, it doesn't invalidate the other one or its history in any way. There's different approaches, BlockNet, ARC, Ethereum, BTC Relay, Parity Poa networks, etc. that do this. And the core idea is that instead of, for example, if you want to transfer assets between two ledgers, you do not look for another individual which wants to trade in exchange to you, but this is handled through some either decentralized sort of third-party mechanism or is actually built into the ledger protocol and ledger network itself. How many of you have heard of Lightning, Raiden? Audience participation question. 1, 2, 3, 4, 5, 6, 7. Okay, now I got a bit more hands up. Started counting. You were all concerned that I will count only to 3. Okay, majority I think then. So payment channels are another mechanism to side-chip a lot of the latencies and transaction costs associated with operating on ledgers. And you could argue that payment channels are two-party side channels created on the spot. If you take a philosophical angle, that's not necessarily how it works. But so let's take for example, on a model where you are doing a lot of transactions on Bitcoin between two parties. So we may be a clearing house between two companies or something like that. And we do a lot of small transactions. And there's a couple of problems in Bitcoin. First of all, you have the long latency. So the settlement times are long. And the second is that each transaction, not only on Ethereum, but also on not only on Bitcoin, but Ethereum and other ledgers, you actually have to pay real value out of your wallet as transaction fees. And that, of course, adds up. So the idea of Lightning channels is that you do most of the operations, most of the transactions between two parties, you and me. We do them, hey, we trust each other. Or actually, we don't trust. We don't have to trust each other. But let's assume that we are honest and work on that assumption and have a backdoor in the case of in either of one is not honest. And the operation is essentially that first we deposit some assets, whatever is necessary. One can do a zero deposit, and then we do this cryptographic shuffle of ledger, and we keep tabs of okay, how much have I paid you? You have paid me this amount. This is our balance between each other. And the cryptographic shuffle here essentially ensures that either one of us can either, if they think that the other party is dishonest, can push back all the transactions back to the ledger. So we have a valid actual operations, transactions on the ledger, which will cost money at that point. Or alternatively, if we are both honest, we can actually settle the whole payment channel at some point and merge it back to the ledger. So instead of maybe thousands of individual small transactions taking years and years on Bitcoin, we get no fees and more or less instant settlement in the payment channel. And the only transactions we need to put on the public blockchain are the initial deposit and the final settlement at the very end. So that's also one way that is easily then extendable. Or you can actually argue that it is a sort of an interledger approach. It's just an interledger that you generate out of thin air for a while. Oh, yeah. Then we get to hash time lock contracts. And just as forewarning, hash time lock agreements and hash time lock contracts are a bit different beast. So let's first talk about hash time hey DLCs. My tongue gets tired of repeating the same long rigmarole. And I actually earlier just described a hash time lock contract. You take something, preimage, hash it, give the hash to someone else. The someone else does a deposit, a time block contract call with the asset and the hash. And the only way you can retrieve the asset is by posting publicly the original token you have, the preimage you have. And the preimage can be arbitrary thing. The preimage can, for example, be signature agreement or something else. But anyway, when we are talking about hash time contracts, we are specifically talking about smart contracts as an implementation medium. And the difference between hash time lock contracts and hash time lock agreements is a bit subtle one. But hash time lock contracts can be used to construct hash time lock agreements. But hash time lock agreements, in the sense that Internet Ledger Payment Work Group introduced them, is a bit subtle and contains situations and use scenarios where there is actually a financial risk involved. The benefit of hash time lock agreements and ILP protocol in general is that you don't have to have smart contract capability on your ledgers. It works even with bank accounts. Or you could argue that it works with manual ledgers like, pen and paper ledgers also. There's different types of HTLA, conditional payment channels on ledger host, escrow, simple payment channels, ILPs, trust lines, etc. But overall, when we talk about HTLAs in general, the agreement in that can mean an agreement between you and me on paper, a legal contract, a legal agreement, just saying that if you do not honor this protocol, I will sue you. Versus hash time lock contract is an enforcement mechanism that does its automatic stuff automatically anyway. And in the context of ILP, I'll come back a little bit later, there are business risks that can come out of those agreements and need to be considered as part of that. And that are not solvable on ledgers, essentially. Here's a quick classification of HTLAs. Not going to go too much into the detail, but there are some trade-offs on different levels on bilateral risk, complexity, and ledger, whether you need actually high level of support from the ledger or whether you can do with low level support mechanisms. That is smart contracts in practice. Okay, hands up. Okay. I didn't realize there's autoplay on that. How many of you don't have a grasp of how has time lock contracts work? Sorry, of course no one is going to put their hands up. How many of you understand how has time lock contracts work? Okay, so quite a few don't understand, so I'm going to use some time to explain this thoroughly now. Now let's try again. How many have a grasp of how has time lock contracts work? Okay, a bit more people now this time. Okay, anyway, we go through, you announce the intent to pay, you go through there, send a hash, random number, whatever. It can be actually a valuable information also. You sort of bring promise to the middleman or smart contract, binding promise, execute. And the execution is part of actually providing the information necessary for sort of the pre-image of that hash. I don't think that helped much. But anyway, ledger of ledgers. Anyone heard of Cosmos or Polkadot? A few people. So Cosmos and Polkadot are sort of ledger of ledger approaches. With the idea that you have sort of a super ledger that is then responsible for bridging the different ledgers together. And I think the idea in general is a brilliant one. Like any have you seen the XCD cartoon of Death Star project, where Darth Vader gets a project manager happily saying that we have 99 Death Star projects that have failed. And the Darth Vader said, let's have another Death Star project. And the next strip is, we have 100 failed Death Star projects. Repeat. And I think this, my personal view is this ledger of ledgers have a bit similar situation, that they are trying to solve a too big problem in one piece. Beautiful idea. But there's sort of the underlying political problem is that why would anyone care about a new super ledger or any ledger, or how would you actually trust this? And in that sense, it is mostly not about the technical issues when you're talking about ledger, Cosmos, and Polkadot. It's a political problem. It's a governance problem and political problem. And you can say whatever about the technology. I don't believe the technology matters. It can be perfect technology, but it can, and I believe it will, in one way or another, trip on the politics. I do have a bias on this also, to be honest. But that's the overall idea, that if you want to transfer funds from this one to this one, you don't actually do that directly, but you have some sort of a meta ledger or super ledger in between where you actually reconcile these transactions. And of course, in this case, the super ledger would have all these rules for governance, etc., and so on. And as final, present a final one of the different interledger approaches. How many of you have heard of, again, the W3 World Wide Web Consortium Interledger Payment Working Group? At least one. Okay, so there is actually some, like this one, standardization effort. There's actually an ISO working group also working on blockchain standards and stuff like that. But they try to actually define sort of a protocol or mechanism where you could bridge multiple ledgers, and they actually include ledgers in the sense of bank ledgers also in this. and the goal of ILP, specifically the Interledger Protocol, which is used to do interledger payments. So you have ILP and ILP. This is hugely confusing sometimes, whether you're talking about Interledger Protocol version something, there's multiple versions of that also to add for the confusion, or whether you're talking about interledger payments, ILP again. But the general idea of this ILP group is that they define a set of protocols, like a bit like Internet Protocol, where they've drawn their philosophical approach from, that then is used between ledgers to facilitate these transfers. And then you have independent, like these connectors. You can have, for example, you can have connectors between Bitcoin and Ethereum, and another connector between Bitcoin and Ethereum. So there is no centralization of the connectors. They are independent businesses, independent groups operating on their own policies. So that's still nicely decentralized. And the ILP protocol itself is more or less a mechanism to route across different connectors these payments. And the ILP specifically focuses on payments. They don't support any kind of other types of cross-ledger transactions or smart contract calls or anything like that. And again, they use HTLAs, has time lock agreements. One of the features of ILP is that often these connectors actually need to share some of the business risks. So the way the protocol and the reconciliation are actually defined within the ILP means that there is actually financial risk, delay risks associated with just being a connector. But the core idea in this case is that let's solve 90% of the cases with code, and the rest we just hope that we can shove under the rug using argument that yes, these companies will manage the risks using conventional methods. Feasible? Will that happen? That's another question over the time. So we are getting to the end soonish. So if you think about just compare these high-level approaches like swaps, sidechain bridging, ledger of ledgers, ILP, and ILP version 1 and ILP version 4, which are different. So, for example, if you think about these, when we're talking about swaps, it's an exchange versus sidechains, bridging, and ledger of ledgers are like value transfer mechanisms. The trust mechanisms also differ. You may have hash and time locks, federated dignitaries, has some sort of smart contracts, additional stuff over this side. And then anyway, when you're operating on any kind of ledger, especially public ledgers, you have to be aware of the transaction costs. And this is one viewpoint, for example, of ledger and ledger approaches, that there is risks associated to this kind of monopoly pricing mechanisms and centralization. Okay. Some typical use cases we already talk about, or I talk about these asset transfer exchanges. But there's also other interesting use cases like connecting consortium ledgers, synchronization, and moving digital collectibles. So I guess this one we already talked to death. Let's skip that. The practical example that I showed is actually an example of connecting sort of a consortium or private ledger with a public ledger. But I believe that the more companies invest in ledger technologies and they may take them into use, they will run into situations where they need to operate across different companies. And eventually, when you know that large companies have multiple copies of the same system, just a little different, that eventually companies will find that they themselves have multiple ledgers, and they have to figure out how to make them interoperate. For example, one possible use case in consortia ledger is that you periodically checkpoint the state of the private ledger to public ledger. Create sort of okay, here's a state hash, let's put it to public ledger. We are pretty sure that no one will hack Bitcoin or Ethereum. Even if our internal consortia ledger is hacked, we can use that checkpoint as a trusted point if something bad happens in the future. So this is very trivial, very simple interledger operation, but that already offers quite a lot of trust value for different kind of consortia. Similarly, you can have a situation where you need to synchronize state between ledgers, sort of try to do some sort of atomic cross-ledger operation, so make sure that you have the same state. What that state is, very much open to use cases, but okay. Anyway, we are getting to the end of this presentation. So if you think about, if you have heard of CryptoKitties, you know that they exist on Ethereum network. So one of the things is, of course, a concern that is Ethereum network forever. So it's easy to think, yes, it's been already for many years. What about 20 years? 40 years? 50 years? These may not necessary, but may become hugely valuable collectibles in the future. But how do you retain their validity if the Ethereum as it currently exists ceases to exist in 30 years? You would need some mechanism to transfer them securely in a way that everybody agrees also is the correct way to do that. CryptoKitties is a fancy example, but you can argue this for any kind of long-lived asset, long-lived record of transactions that may need also have a legal requirement for being retained for a long time. So if your sort of legal or auditing requirements are currently met by a ledger, even if it's an internal ledger, what happens if when your IT department says that the cost of maintaining this is prohibitive, we want to get rid of it? How do you retain the transfer of immutability across different ledgers? So that's some of the problems that will need to be solved in some way or another in the future. That I don't really know what are the solutions going to be there, but they will most definitely fit under the label of interledger. So in summary, there's quite a lot of reasons why to think that interledger is or will be important for operating ledgers, at least on business scale and not only on research scale. There's many approaches and approaches to these different mechanisms. Some are quite accepted and well known how to operate, like HDLCs. But it is definitely a research field, and there are going to be definitely developments in the future that will change some of the assumptions and models that we have currently here. But eventually, I think that given the technological advancement and also the proliferation, sort of this huge outgrowth of public blockchains, and the eventual growth of company, consortia, and private ledgers will lead to a sort of a classic situation of interoperability and interconnectedness, and how to retain these security properties even across migrations and everything. So I would, if you are as old as me, you may remember token ring from IBM from 80s. and the competition between Ethernet and tokering and stuff like this. So I think currently technologically ledgers are sort of in the same level of late 80s technology when you have token ring, FDDI, ATM, Ethernet, and it was not clear that Ethernet is going to become the dominant technology. There will be eventually some mechanism to make all of these things work together. What that is, it's still so far in the future that I don't dare to gaze into that crystal ball, but I believe that it will be called Interledger something. So that's my presentation. Thank you, everybody, for your time. And it seems that I'm a bit early on schedule, so if that's okay with you. Any questions?
So you're talking about two platforms when they are communicating with each other and sending transactions to each other.
Yeah.
So as you said, one can be a private, another can be a public platform. In that case, I see that there will be differences in the performances of the two platforms also.
Yes.
So either the performance, the transactions will stack up or buffer up at one end in that case, if you think of scale.
Yes, that is a definite problem. I would also argue that it is a case-by-case problem. It's a business problem, and of course, if you have the underlying requirement that you have to transact on Bitcoin and receive payments on Bitcoin, it will be very difficult to get around that. Of course, then you can start using sidechains, payment channels, trust lines, all of these other mechanisms to speed that up, but then we sort of venture already into the Interledger sort of cubed region. And you notice that you correctly pointed out that I've been talking about two ledgers all the time. It is entirely possible to have more than two ledgers sort of committing together, so 3, 4. Of course, any kind of multi-party computation gets more difficult and error-prone the more parties you add to that. But it's most definitely have, for example, across two ledgers and a private ledger operations.
Okay.
So in the design that you have shown, between the two ledgers, there was a gateway who was basically maybe transforming the transactions to finally lead to the successful transaction between the two ledgers. So was the gateway specifically has been designed for some specific platforms, or would it be generic enough to take care of any two different ledgers? Is it still a theory, or have you implemented it for some?
Well, this is an example, a necessary research project, particularly that I'm working on. And of course, one of the things that we are researching is to understand how generalizable these solutions are. I hope that we will have some results on that eventually. But, okay, autoplay. I hate autoplay. Anyway, previous one, this one. So, and eventually this is the one that I'm demonstrating out there. But in this case, the gateway sort of is just shuffling things back and forth. And as I said, and I will say also out there on the demo that this is highly trivialized and has tons of security issues. I'm not trying to create a secure system, but a demonstration, a proof of concept system here. But generally saying, it depends on the use case. So in this use case where we are essentially saying, how do I disable that? Well, where is the option to disable that one? Okay, maybe I'll just keep my hand on the back button. Now I remember I was trying to get this work earlier, and it's here. Normal presentation, not autoplay. Now it should work. So this particular one is, you could say, a very, very stupid gateway. It essentially takes events from this side, shuffles them into smart contract on this side, these call the smart contract, which generates events, which this detects and shuffles them again out this side. So that as a general concept is highly generalizable. However, whether that is sufficient for a use case is a whole other thing. So this is a singular gateway, but it is not secure because that singular gateway is centralized, and of course we would want to do away with the centralization, so maybe we need a federated peg. But if you have a federated peg, you have multi-party signatures and all the protocols associated with that, and agreement protocols, etc. So sort of it is easy to create a trivial non-secure version.
So even when you say it would be generalized, you are planning to build a generalized version, it would still be generalized for two set of ledgers, say for example an Ethereum and a Fabric. But when, say for example, multi-chain comes, there would be design variation in the gateway, right?
This goes somewhat to the discussion that I think my colleague from Ericsson is going to have a panel discussion in a few days about the development and interoperability and standardization of blockchain protocols. But essentially what you have, the problem is that the SDKs and the protocols that are in here and in here are absolutely incompatible. And if you want to talk with Ripple, you have to code for Ripple. And there's no that kind of interoperability currently existing on the sort of the programming level at all. Not to talk about Interledger at all either. So that's a practical problem. I see why that would be highly desirable, but currently it is incredibly difficult to implement even these kind of setups because of the deficiencies in the tools available. I can tell that I grew to have a hate relationship with Fabric while doing this.
What we're talking about here is connecting up different systems, which have got very, very different semantics with respect to what exactly the consensus protocol is providing you, particularly in the case of the ones that operate probabilistically. Right? And some of those, we're still trying to understand what the spec of the protocol actually is giving you. And now we're talking about connecting things. So where are we, do you think, with respect to understanding when we have these combined systems, what is the semantics of that going to be in terms of how the sort of consensus I mean, the protocols that you've talked about, I think, talk about the ideal case for each of the underlying ledgers, right? Now, what if something goes wrong? There's a fork on one of those ledgers, for example, or reorganization, or one of those protocols is running not in their ideal case, but in some imperfect case. And what happens to the semantics of the combined system?
I think the default at these days, that I'm operating on, and most people are still operating on, is just let's hope that never happens. Let's kick the can down the road. There's quite a lot of other practical problems currently here, but you are entirely right that it is a thing that needs to be addressed. And forks generally are very difficult things to handle. And let me take an example. I've been working on actually skipping this gateway and talking from here to directly to here, even on highly constrained devices. And the mechanisms that are needed to handle forks and joins it's just mind-bogglingly complex to get around. So my answer to that is personally, I don't want to go there terribly too much. But you are entirely right that it is a problem that cannot be bypassed, at least on any kind of a realistic timeline.
Yes, I have a question so about the Interledger. So what kind of throughput to help us evaluate that this kind of Interledger is better than the other kinds of Interledger? So what kind of throughput to evaluate?
So first of all, it depends the performance of a ledger depends on the performance of the ledger. So if you are using a specific ledger, you will be, first of all, stuck to it. So if you are operating on Bitcoin, you will have a long confirmation delay and even longer commit delay. And that's sort of the reality problem, the problem of reality, that there exist these ledgers which have a huge market capitalization, and if you want to operate on them, you can't change them. So you have to work around that problem. So for example, on the demonstration I have set the, while it's a proof of authority mining network on Ethereum, I've set the block interval to 15 seconds. So whenever I demonstrate something might happen in about 15 seconds or about 30 seconds because it requires two transactions to operate. But the Hyperledger goes like chup, chup, because it has an immediate commit.
Yes, thank you. And then so to develop an Interledger, so what is the challenges and time consuming to develop the Interledger?
I would say one problem currently is to define a use case. So where to find a realistic use case that actually makes more sense than just as a toy problem. So I'm pretty happy with toy problems because it is still a field that is ripe for even that ground level research. But on the business side, you do need actually a working business case first, and I haven't terribly seen those. So you probably have noticed that a lot of the benefits of cryptocurrency, etc., from convenience point of view, being used to conventional banking, are not terribly convenient. And the same applies to any kind of interledger approaches until you find sort of this killer application or whatnot. I would say that the challenge is often on that level, unless you're happy with doing sort of a ground research, just making sure that things work and it is possible to do these kinds of things, which I'm happy as a groundhog personally.
Yes, thank you very much. Just a final question. So do you know any, Interledger that's available for business yet? Or maybe a research model? It's, complete one.
So, for example, the Lightning and Raiden payment channel networks actually exist. The technology exists and it is available for use in Bitcoin and Ethereum. Sidechain implementations exist. So if you want to transfer, if you find, for example, a sidechain that you would want to use, that exists somewhere, then it's actually possible to transfer your Bitcoin assets or some of them to that. So those actually work. Hash time lock contracts themselves are, there's probably some like template code available, but those are like so low level primitive that they are pretty straightforward to implement, because there's like, if I look literally at this, the smart contract code I wrote there, most of the lines come out of comments and nice coding style and not the actual code. So it's pretty compact in that sense. But on the other stuff, such as Cosmos, Polkadot, there's a lot of development there. But how you would actually use that code, that's a big question. So talking about maturity levels of these technologies, I would say that payment channels, sidechains are probably most of the major technology, and there's most of the sort of ready-made solutions already available on those. Polkadot, Cosmos, nice concepts, not much of useful stuff. ILP has nice demonstrator PCs, but it hasn't really been deployed in production at that level that you would, anyone actually more or less would find it useful. And on the other levels, has time lock contracts, you have a lot of sample code that you can apply. A lot of that is open source also. Did I miss something? Okay.
Yes, thank you very much.
Thank you. Thank you. Okay.
I think
So
the
if that's
time
it.
is up.
Thank you.
And I'd like to thank the tutorial speaker once again. Thank you very much for a wonderful tutorial.